He's a famous editor, journalist, author, was editor for Scientific American, editor-in-chief for American Scientist for a number of years, and wrote a column for them for many years. He's written a number of books in the area of mathematics and computation, including group theory in the bedroom and other mathematical diversions, and foolproof and other mathematical meditations. And we're very pleased to have him here as the journalist in residence this semester. Maybe I should say the aim of the journalist in residence program, it's both for outreach for the Simons Institute, but also to give the participants in programs communicating their results, and you know, that's what we're going to hear about today is communicating computational science. Brian, welcome.
Thank you, Peter. Thanks very much, and thanks to everybody for coming to this. I'm going to be talking about some things that sound like tricks of the trade for science writers and might seem rather narrow. I hope to persuade you that they're not, that in fact this is all about how people communicate with one another, how they teach, and especially how they learn, applying this to myself as well as everybody else. Please feel free to interrupt with questions or, heaven forbid, corrections. I don't mind at all if this degenerates into a dialogue rather than a monologue. Anyway, to begin with, these people are simultaneous interpreters at the United Nations. And I first, as a school child, visited the UN and put on the headphones and listened to what they were doing, and I was utterly amazed by it, and I still am. You have to realize that they are executing a streaming algorithm. They take in a couple of phrases and have to produce a translation of that before they even hear the end of the sentence. This is a very impressive performance, whether you view it as an algorithm or as a neural process. And I'm just full of admiration for them. This process has also sometimes been proposed as a kind of analogy for what science writers do. That is, my role as Snoopy is to listen to some deep thought expressed in the jargon of mathematics or some other field, and then I apply a magic function to it of some kind. I transform it into phrases of very simple words that anybody can understand. So everything's, whoops, wrong button. Everybody does that. Everything's flowing from over here through me, and then, whoops, I've got the wrong slide here. Yes, and flowing this way. And I don't think that's actually how it works. I don't think that's what I do. I don't think I could do it, for that matter. I don't have this magic function that transforms gobbledygook into plain prose. What I do have is the ability to listen to somebody and try to figure out what they're saying and form a mental representation of what the whole discourse means. I can't do it one phrase at a time, and I can't do it simultaneously. But if I spend a few weeks or months or occasionally years, I can figure out what's going on over there and form my own model of it. And everybody else can do that too. That is, over here, my readers are capable of forming their own representation of whatever the subject is. And in fact, they haven't really learned anything or understood what I was saying until they do so. This is, the key arrows here are the ones that go up we all of us learn not by having someone pour knowledge into our ears, but by working through problems, making mistakes, trying to go through some of the steps that the original author did. In order to write about science, I have to do that. I have to work at understanding what it's about. And my readers, the point of my existence is to try to make it easier for them. But there's no royal road here. Everybody has to work and create their own knowledge structure. I'm not the only one who ever said that. Keats's version of this has always struck me as right on the mark. He could be talking about mathematics. That you can read fine things, but you never feel them to the full until you've gone through the same steps as the author. It's not enough to just read it. You need to do the problems at the end of the chapter. So the question is, what can we do to make that process less painful and more effective? And I've got 3 words in the title there, and these are the tools that I'm going to mention. There may well be more. Words are kind of the obvious choice here, and I'm actually not going to say very much about them. I mean, if you ask a writer, or even a non-writer, what does a writer do? The answer is that you string words together one after another, and if you do your job well, you've put them in the right order. And this is all true. Words are the primary medium for communicating pretty much everything in this world. But I'd like to emphasize the other aspects of this. I think, as this nonsense will demonstrate, putting the words together is actually the lowest level aspect of being a writer. It's not how I spend most of my time. I spend much more time learning than writing. Furthermore, it's probably the part of my job that could most easily be automated and put me out of business. What you're seeing here is actually the archetypal Markov chain. In 1913, when Markov first created the process that we now call a Markov chain, what he was dealing with was finding the conditional probabilities of letters following one another in Alexander Pushkin's poem Eugen Onegin. And that's exactly what this is doing here. It's just looking at, I think, 4 grams or maybe 5 grams. If Markov had had a computer, he would have written this very program. I'm absolutely convinced of it. He had to do it by hand. So anyway, words are irreplaceable, but let's move on. I hope we can move on to pictures. Words and pictures together, in fact. This has been an aspect of written communication going back to the beginning of writing. This one happens to be the Oliver Burns edition of Euclid's Elements from the middle of the 19th century. It's an extremely peculiar book, but has this wonderful device of putting words and mathematical notation and pictures all mashed together in the same narrative. And it works. That is, you can puzzle this out and it makes sense. I mean, this is the proof of the Pythagorean theorem, or part of it. It's an art form that has not disappeared, but has been suppressed to some extent. This is even older, 1,000 years old, from Avicenna. I'm not actually sure what we're looking at, but I think, I think we have two eyes and the primary visual cortex here. Although I don't read Arabic, so this is conjecture. Another way of putting words and pictures together that's very popular is the comic book, or to be more pretentious about it, the graphic novel. This one is co-authored by none other than Christos Papadimitriou. This is Bertrand Russell's moment of epiphany when he thinks about the set of all sets that don't contain themselves. I find the device of mingling words and pictures as closely as we can to be actually very attractive, and I wish we had better ways to practice it, and I'm hoping that as we move away from paper publishing toward the web, we'll get back to it some. This is an exercise in words and pictures that actually taught me everything I know about it. This was the first issue of Scientific American that I contributed to. You can tell how old it is by the fact that the chip there, which was then worth putting on the cover of a national magazine, is a 4 kilobyte memory. Anyway, we put a whole lot of emphasis on illustrating. An editor's time at that magazine, at least half, and often more than that, was spent not twiddling with words, but creating pictures. And you can see in this article, which is also by Christos Papadimitriou, that roughly 2/3 of the space is given over to pictures rather than words. However, something's been lost in that all of the illustrations are in little rectilinear compartments with text that accompanies them, and you have to read the text and then look at the illustrations separately. This has become the norm in almost all academic publishing now. I mean, you have, as I'm sure all of you know, if you write a paper, you have a list of figures and they're numbered and they get placed in the manuscript. And the idea of being able to have a close dialogue between words and pictures has become more and more difficult. So, leaving behind the words and pictures, I come to the third medium of communication here, and it's the one that I feel is most in need of attention. Let me say this is another article from, not from Scientific American, but from American Scientist, and this is one of my own. And we're still dealing with pictures in boxes separate from the text, except that I've managed to sneak in a couple of little inline illustrations here. But the one I want to talk about is this one. And this is, in fact, it has no place in a printed magazine. It's a screen capture of something that's running on a computer, and it's a very dynamic object. And pasting it down on paper and making it static is kind of criminal, because you have a hard time understanding what's going on there. Unfortunately, for paper publishing, there's no choice. There's no way you can animate it. But just because it has to be that way on paper doesn't mean that we should have to do it when we publish online. So this, in fact, is the thing itself, the thing that was captured. So this has to do with, let's make it more fun. This has to do with Braze's paradox, which was mentioned in this room a week or two ago. And it's a dynamic simulation of a network that's closely related to the one Braze described, although certainly not identical. I don't actually want to go into what this is about and what we can learn from it. I think there is something interesting happening here, and it's worth observing, but that's another talk. My real point here is that if you want to show your readers something of this nature, something that's dynamic, it's got to be in this format. You need to present it to them in a way that they can actually see it run, not just talk about it. I'll let that finish up. Well, actually, I will say something about what you were looking at. What I found interesting the very first time I started running this is the pattern of oscillations. This is the number of vehicles of each color that you were seeing as a function of time. And there's an obvious alternation here when there are only the two kinds that are on the road, where you have one thing building up and the other falling away. When you have four different routes being traveled, there's still an oscillation. It's got very complicated correlations and anti-correlations. So I do think this is worth investigating, but it's not today's topic. Today's topic is, in fact, the Ising model of ferromagnetism. Does everyone know the Ising model, or no one? Anyone? I see. Yes, quite a few. Okay. So I'm going to try to go through what I think is a plausible attempt to explain what this thing is about. Those who don't know it will be the guinea pigs in this process of trying to communicate something. Those who do know it, you can keep me honest. Speak up if I'm talking nonsense. This is, or began as anyway, a model of ferromagnetism, the magnetism of the kind that sticks to your refrigerator or these whiteboards. And I, from childhood, have found it utterly fascinating. I mean, you take these little magnets and you try to force them together and you can't. Or you put them on the table and they chase each other around. This is utterly mysterious. I mean, the fact that we're very familiar with it after a lifetime of seeing such things shouldn't really detract from the fact that, you know, there's something invisible that's nonetheless very tangible. You can feel it in your fingers. And there's nothing to see. And it doesn't go away. You know, it doesn't seem to require energy to maintain itself. Fascinating phenomenon. And so, you know, how does it work? Where did it come from? By the end of the 19th century, there was a sort of gathering consensus about one thing in the study of ferromagnetism, and that's that it was some kind of collective phenomenon. Not that when you magnetize a piece of iron, you suddenly create magnets in it, but rather that it's full of little magnets of some sort, and when you magnetize it, what you're doing is you're lining them up in parallel. So the hypothesis then was that if you have two of these small magnets, which were soon identified as electrons, electrons with spin. If you have the spin vectors, these things parallel, the energy of the system is lower than if they're anti-parallel. And So the question was, if you simply start from that hypothesis, can you explain the observations of real ferromagnets? So this was, we're talking the early years of the 20th century when quantum mechanics was just a morning. And there were some fairly wild ideas about what might be going on. In the Ising model, it was recognized that the interactions that cause that alignment have to be short range. And in the model itself, they simply made the simplifying abstraction that each spin communicates only with its nearest neighbors along the dotted lines of this lattice. And for graphic convenience, there's no need to draw all of those little arrows, which are very hard to make out. So the arrows can be either up or down, so you simply replace them by two colors. It's just a binary variable. So this is the phenomenon that the model was meant to explain. That if you take a piece of iron and heat it up to 1,000 degrees or so, it loses all of its magnetization. If you then cool it at a low rate, all of a sudden it reaches a critical temperature where it begins to spontaneously magnetize again. So you want to explain that in terms of the microscale spins within the substance. And here's what you can get for the kind of smallest non-trivial Ising model, where we take a block of 4 spins arranged in a square, and you can calculate their magnetization, which for each of these spins has effectively 2 neighbors, because you're only looking vertically and horizontally, not at the diagonals. And you count, in magnetization, you simply count the number of spins that are identical. If you have 2 and 2, it's 0. If you have all 4, it's either -4 or +4. At the same time, you can calculate the energy of these configurations, because if the neighbors are of the same color, you get a negative contribution, which adds up to 4 of them in this case. If they are of opposite colors, in this case you've got 4 pairs of neighbors that are all opposite, you get a +1 for each. And these all balance out exactly. So in this scheme, we have magnetization along this axis, energy along this axis. And what we really want to know is, of these 16 possible states for a 4-member plaque, what's the likelihood of seeing each of those? And it depends on temperature, because we have a thermal situation where you're introducing disorder by thermal fluctuations that can cause the spins to flip. And for a system of this size, you can calculate it exactly by hand. There are 16 possible configurations. You calculate their energy and can immediately find the probability of each state. At high temperature, it's pretty flat. At low temperature, these magnetized configurations become overwhelmingly the likeliest to see. In this case, it's about 1/4 each. Here, the yellow line is an exact calculation, and the bars are simulation results. So all this came about starting in 1920. Wilhelm Lenz in Hamburg actually invented the model that we now call the Ising model. Ising was his student, and he took it up and did his dissertation on it. He's an interesting story. One question has always been, how do you pronounce his name? And the answer is any way you want, really. When he was a German, he was Ising. He later, after some hard times in Nazi Germany, he later washed up in the US, and where people called him Ising, and he didn't mind that at all. And in fact, when he became a citizen, he changed his first name from Ernst to Ernest. He lived 98 years to the day, and I could kick myself that I never met him. He was right there in Illinois. I could have looked him up. I didn't know he was there. I didn't even know he was still living until he wasn't. This was his publication on his contribution to the theory of ferromagnetism. It was his only publication. He, as I indicated, had a hard time making a career. And what he worked on was strictly the one-dimensional version of the model, where you just have a line full of spins. And he found that, in fact, there is no phase transition. There's no magnetization. And this was a correct result. I'm lying a little bit here. It's not quite as simple as this, but one way to think about it is that if you have this fully magnetized state where all the spins are parallel, and then you flip this block, the half of them, you now have zero magnetization. But the only contribution to the energy is this one pair that are now antiparallel. And if you take the limit as this chain becomes infinitely long, that's a negligible energy difference. The two things are essentially the same. So there's no tendency to magnetize spontaneously. And Ising thought, and in fact wrote, that this was a flaw of the whole model, that lack of a phase transition would also carry through into higher dimensions. And other people disagreed and ultimately showed that it wasn't true. The big push here was by Lars Onsager, whose paper I have tried to read, I don't know, once a decade for 40 years now. And I get parts of it. It's very difficult mathematics and kind of old-fashioned mathematics at this point. But there's no question he did prove it. He solved the model in the following sense, that he came up with an analytic analysis of this system in the case where it's infinite, that is in 2 dimensions, goes on forever. It's a square lattice, and there's no external field. And given those conditions, he was able to basically give us a formula for knowing anything you want to know about the whole system. In particular, he identified the critical temperature. We're measuring temperature here in dimensionless terms. Boltzmann's constant is 1. And he showed that the magnetization, that curve that looks like this, is actually, it's the temperature difference from here to here to the 1/8 power. I don't know of another 8th root showing up in the physical sciences, but maybe there is. Beyond 2 dimensions, things are still very murky. There have been claims of solutions to a 3-dimensional model. As far as I can tell, nobody takes them seriously. We have lots of simulation results for it. In very high dimensions, it turns out it's easy, that it becomes a mean field problem, that you're talking to so many neighbors in high dimensions that you can basically just assume that everybody feels the same average force. And the model has taken on a life of its own. This started out as a way of explaining ferromagnets. It very soon was recognized that it's identical to the problem of understanding disorder in metallic alloys and some kinds of fluid phenomena. It's turned up very widely since then. The Schelling model of residential segregation is essentially the Ising model with people instead of spins. And there are well-known applications in the neurosciences. It's gotten really to the point where the model is not a model of anything. It's an object of study for itself. You don't necessarily care what it represents. There are several thousand papers on it, and lots of generalizations and specializations where you take a different lattice or more spins, or where instead of having the coupling between adjacent spins always the same, you randomly make some plus and some minus. So at this point, for the two-dimensional model, it seems like we're done, that we have an exact solution from Onsager. We can calculate what we want. You tell me the temperature, I can tell you the magnetization or the magnetic susceptibility. For me, however, I'm not the least bit satisfied with this. Being able to calculate is great, but I want some intuition about what this thing looks like, how it works. I want to be able to internalize what's going on there. And furthermore, the solution only tells you the equilibrium state. That is, if you wait long enough, this is what it's going to look like. Long enough may be eons or something. It doesn't give you any dynamics about how if you're at zero temperature and you suddenly turn on the blowtorch and you raise the temperature, it doesn't give you the tools to say what's going to change and how it's going to evolve. And I find it, kind of haunting that all of these people for 3 or 4 decades who worked on this thing, spent whole careers trying to solve it, they never actually saw an instance of an Ising model. I mean, there was nothing visual to go on, not even a snapshot of some state of this lattice system. It was all done strictly in their heads. This was my very first glimpse of what an Ising model might look like. And it was a curious story. I was working with Ken Wilson, who was then at Cornell, on this article at Scientific American, and this was one that took a solid 3 months. And the Ising model was a big part of the story. And he very helpfully explained much about the analysis of it and his computational approaches to studying it. And so I asked, can we have a picture of this? What does it look like? Can you show me what the lattice looks like at various temperatures? And he said, well, I have no idea what it looks like. I've never seen it myself. Let's try to find out. And so he got his friend down the hall, Jan Tabachnik, to write a program to actually generate pictures of the thing. Although the pictures that he produced did not look like this. He sent me a box full of green bar fanfold paper covered with ones and zeros, many thousands of them. And it was the fate of some poor typesetter We handed the ones and zeros and had him type them into these black and white characters. I never met the typesetter, and it probably curses me and my family still. Anyway, so not only did I finally get a glimpse of this, but so did Ken Wilson, who had been working on it for years. And so this is high temperature. I think it's twice the critical temperature. This is slightly above, and this is at the critical temperature. So this was, this was 1979, I think. Not too much later, I finally had the wherewithal to compute the thing myself. And so this was the first Ising model that I actually computed. I made a terrible choice about how to present it because those arrows are uninterpretable. You can't really see what you're looking at. I was supposed to be the guy who knew graphics. What a mess. There's also actually a serious bug in this program, which is another talk for another time. But so 10 years later, this isn't actually the Ising model. It's a variant that has more than 2 spin directions called the Potts model. That's why the multi-colors. But we're doing the same thing here. We've got high temperature, medium, and low temperature. And you sort of learn to recognize those things. Another 10 years pass, and this is another one I did, and I decided I was tired of the 3-panel business, so I put a temperature gradient across this rectangle, and so we have temperature varying continuously from high to low across there. I've never been sure that that's really kosher, but I didn't hear any complaints. But my point here is that looking at those still pictures is still a sort of a very difficult way to get intuition about what these things look like, because they're not still. Even if you recognize the isolated state of the thing at a certain temperature, you're seeing a snapshot that it's like looking at a photograph of a horse running. If all you see is one instant, you don't really know how a horse runs. So obviously, I'm going to fix that. Here's a simulation we can play with in a web page. So we're at sort of medium temperature. We'll go up to high temperature. And this is not still. This is, you can see that the pattern in some sense is persistent, but if you look at any one cell of this thing, it's clearly anything but stable. Go down to the neighborhood of the critical point, try to get there. This is why I brought the mouse. That's close enough. And you see what Ken Wilson was writing about, in fact, is that you see fluctuations at all spatial scales here. We're getting big ones that span the entire space, but the small ones are still there as well. And this is what makes things difficult to calculate. And if you go down to low enough temperature, you get into this blobby regime where only the large-scale slow fluctuations persist. This one actually it could go to a completely magnetized state, but it's not going to, and I'll come back to that in a moment. So just briefly, what you're looking at here, the square is actually a torus. It wraps around side to side and top to bottom. So there are no boundaries within the system. This is obviously an arbitrary choice. You can do whatever you want with that. And the algorithm being used here is pick a spin at random from anywhere within the grid. If flipping it would reduce the overall energy, do so. if flipping it wouldn't reduce the energy, maybe you flip it anyway, and that's determined by this Boltzmann weight, which is, says that the higher the temperature, the more likely you are to do the flip, and the greater the energy imbalance, the less likely you are. So a few minutes of looking at this tells you a lot about what you're likely to see. The scale of the fluctuations changes. There's also a pronounced temporal effect in that everything slows down when it gets cold. And another aspect of it is that what you're seeing, no, I won't go back. At low temperature, all the action is in the boundaries between those two regions, between red and blue. This is where the energy is focused. It's the spins along the boundary that are in conflict over which side they want to join. And this is directly analogous to surface tension and has the same result in the same way that surface tension causes droplets to contract into spheres. It turns these regions into blobs. And one result of that, which we were just about to see in the run that we were doing, is that in the analytic model, at zero temperature, this thing invariably becomes completely magnetized. It becomes either completely red or completely blue. But in this finite model, that's not the case. The way it works out is that if you have a row of blue cells right next to a row of red cells, and it's a straight line, then each of these guys has 3 red neighbors and is unlikely to ever flip. And at the same time, each of these guys has 3 blue neighbors. And so this boundary becomes stabilized at zero temperature, and you wind up with these Mark Rothko paintings. It only works with horizontal and vertical. If you have a slanted line, it's not stable. So after all this, do we finally understand the Ising model? I mean, and by understand, I mean, do you have an inner representation, an intuition about how this thing works, what you're likely to see? Those of you who were not familiar with this before, have I had any success? Yeah. +1, okay. I'm not going to ask any further. I feel that, this is a huge advance. Having the technology to put the simulation itself in the hands of my readers or my listeners, this is a huge improvement over what it was when we were working with ink on paper. At the same time, I feel it's only like half the battle, because when I look at how I learn things like this, in particular writing simulations like this, where I learn is not from running the program. I can often throw it away as soon as it's finished. Where I learn is from writing the program, from creating the simulation, from solving the problems that come up along the way. And that whole process, that's the creative part. And that kind of creativity, I think, is an essential part of learning. And so, I have to ask, can we somehow put the reader in the position of having access to that experience, of actually creating something, something fresh in code? Well, to do it fully, I mean, basically you have to do it yourself. That's the point I'm making. And I simply have no role in that. If there are people out there who are sufficiently motivated to do so, but it's kind of a tough thing to do, is to say at the end of an article, if you really want to understand what I'm talking about, you got to go do everything I did again. So this kind of next best alternative is to provide my program in a format where other people can dig into it, change it, fiddle with it, play with it, break it. And that has been something I've been trying to do for decades. The problem initially was just one of distribution. I could write at the end of an article, if you're interested in this and would like to play with the program, send me a floppy disk and I'll mail it back to you. This actually happened. I mean, you know, there were a few people who sent disks, and a portion of those who really did something interesting with it and let me know, and usually had, you know, gotten way beyond my level. A few very good friends I met in that way. But it's still, it's a tiny population who are willing to go that far. Now the distribution problem has actually been solved. We have GitHub. I can just put the code there and anybody can get it quite easily. It's still a pain to try to run it, or even to install it. You know, I mean, at this point in the history of the world, programming is easy. System administration is a nightmare. You know, I've tried to install, well, maybe it's just me, but I think there's a lot of friction. There's a big barrier to entry if you tell somebody, here's the code, all you need to do is install Python and Torch and you're good to go. So the answer that I'm hoping to make work is to put everything, the words and the pictures, the running program and the source code for that program, and an editor that will allow you to modify that source code, put it all into a web page. I've put it into a web page. I haven't yet figured out how to put it into this demonstration. But if you click on the link, by the way, these slides are available. I'll go back to put the URL up again. Everything I'm playing with, you can play with. So this is exactly the same program that we were just running. Does the same stuff, responds in the same way, like so. The difference is that now we can put the source code in front of you. And you can not only read it, but you can do things to it. For example, if maybe you don't like red and blue, too political, so we can just change the colors and do that. And we've got the same thing going, but now it's yellow and brown. Excuse me. And maybe instead of, maybe you'd like more cells in the grid. So you do that, you get something that is really the same but seems to have a different texture. Kind of ants crawling over the picnic table or something. And one can do less trivial things than this. Here's one that's non-trivial or less trivial. But actually, I'm going to first of all go back where we were. Change this from a ferromagnet into an anti-ferromagnet, which is exactly the same model, except that instead of the spins wanting to be parallel, they want to be anti-parallel. Antiferromagnets actually exist. I mean, you know, the real thing, not just in the model. Although, as far as I know, they don't have a lot of uses. Anyway, at high temperature, you'd have to be alert to see the difference of what's going on here. But when it gets cool, you can see that there's something very different. The stable state is not magnetized with all red or all blue. Is this still working? I'm out of batteries. Anyway, doesn't matter. It's a checkerboard everywhere, but importantly, it's not the same checkerboard everywhere because there's a parity effect here. You can have, you know, red at the northwest corner, or you can have blue at the northwest corner, and the rest of it has to conform to that. And what you're seeing, in fact, are again, boundary regions where all the energy is between regions of those two phases. And this also can freeze eventually. I think we're just going to see that disappear any minute now, and you've got a stable antiferromagnetic state. So if I trusted my typing and we had a little more time, I might show you some more tricks, but I think I should finish. How does this process work? Starting point is that here that there's absolutely nothing to install in order for people who want to read my work to be able to just not only read it but also play with these programs. All you need is a web browser. The programs are running on your laptop, not on my server, which is important to me in that I don't have to pay for all this computational capacity. But it's also important, I think, for the people on the other end because it means I don't have to know who you are, you don't have to have an account, you don't have to register or anything like that. The whole thing can be free in both the economic sense and the liberty sense. That, you know, anybody anywhere in the world who can get to a website can do this stuff. I did not create all of this magic. The crucial component that makes this possible is a program called CodeMirror that is the editor that allows you can be embedded inside a web page and allows you to write programs or edit programs. On the other hand, it's not heaven. The only programming language available, strictly speaking, to do this way is JavaScript, which I'm fine with, but not everybody in the world loves it. The process of editing in a little panel within a web page gets to be really a mess when you've got a 1,000-line long program. So this is likely to work best with things that can be broken down into small bytes. And then there are two really serious problems. One is that it's the nature of JavaScript in a web browser that you have no access to the local file system, which means you can write a program to, say, gather statistics about one of these things, but you can't save the results to your own disk. And getting around this is not impossible, but it's a bit of a mess. And finally, and most seriously, if you make a mistake, I have no way to help you. That is, if you type something wrong, the program just stops working. And trying to figure out ways to at least provide some guidance, some error messages, is actually the big challenge that I'm trying to deal with right now. There are other ways to go about this, but I don't like them. This is the project that I'm actually working on. What you see is a kind of alpha demo of what this is going to be. It's a book-length object on the web It's going to be full of things like what you just saw. This is kind of the chapters that come first, at least chronologically, if not in the table of contents. This is all going to be freely available on the web, but don't hold your breath because it's a big project and I'm still in the early stages. These are some people whose work basically convinced me that what I'm trying to do isn't crazy and is possible. And they've done the hard work. I'm trying to adapt it. And thank you all.
Thanks, Brian. Questions?
So I didn't have time to see the list of alternative strategies. Could you
I can go back,
and
yes.
maybe tell us why you don't like them?
Yes. They don't, you know, I mean, why I don't like, that's a very personal thing, but they don't actually meet the criteria. Jupyter notebooks are wonderful. I use them all the time. And they do allow you to basically pick whatever language you want at this point. However, you've got to install it. You know, this is easier now than it was even a year ago. But you're still, you know, the reader I have in mind is someone who's curious, but not terribly adept with things like installing software. And most of all, just, you know, am I sufficiently interested to spend the hour or day or whatever that it might take to do that? So I don't go for Jupyter for that reason. All these others are, they have a different model. The computation is done on a server somewhere. And all these three you have to pay for. I mean, that is, the user has to pay for. They're not expensive. CoCalc, I happen to think, is worth every penny. That's basically the online Sage system. But they don't work for the model that I want to use. There are some other glimmerings of projects that would allow other languages than JavaScript to be used in this same way. It's basically, you know, you write a compiler to JavaScript, and everything that goes into it then gets passed through the compiler. I don't know whether that's, you know, going to be practical. It's amazing enough that, you know, that a language running within a web browser is now nearly competitive with, like, C or Fortran. It's amazingly capable. I never would have dreamed that it would happen in my lifetime. Anybody else? Yes, Manuel.
You mentioned at one point in your talk that you get more from writing the program than from running it.
Yes.
And that reminded me of a quote from Dwight D. Eisenhower, which I have here, which says, "In preparing for battle, I have always found that plans are useless, but planning is indispensable."
I should add that to my list of quotations. Yes, Dana.
You have to be a physicist to like Ising, but Chris Hart, he had a very nice solution to iterated prisoner's dilemma. He had a public goods game where you can play defect or sit out, and with the three states playing on a grid, you can play with the parameters. You get all kinds of different
Ising did this? Ising did this?
No,
Oh.
Ising.
Oh.
No, Ising is, I'm just saying, Ising, you have to be a physicist to like this. But the public goods simulation is kind of fascinating, because you can get these societies where you can have a lot of cooperators and you pay the price of a few defectors, and you can have it. It's very dynamic to see the thing evolve. And
Well,
it'll be a lot of fun.
Yeah, I agree with you. I mean, you don't have to be a physicist to love it, but the fact is,
It helps.
It has been reinvented dozens of times, especially in the social sciences, by people who never heard of it. You know, Thomas Schelling with his little racial segregation model, it's isomorphic
No, I
to
think
the
it makes
thing.
your point. It's
Yeah.
spectacular, but
Yeah.
I'd be curious to see what the public game simulation would look like. That would be fun.
Let's do it.
Okay.
I mean, you know, it's probably just a trivial change to what we have already.
Yep,
So,
I think so.
yeah. Yes.
It's a great talk, just a nitpicking comment. I think the Chinese verb was actually not a Chinese verb.
I had a Chinese verb?
The proverb that you showed at the bottom?
Oh, the proverb. Oh, it's not a Chinese proverb.
So it's an erroneous translation.
Okay.
And it was like the Western interpretation of.
I would love to know the real version. Yes, I'm going to be impolite enough to tell you where I got it, so that you know it's not my fault.
It's a famous Western sentence, I suppose, but it's always been attributed vaguely to Confucius. It was Confucius, but it was a wrong translation.
I love to be corrected about things like this. Yes.
We should
We have food.
keep the discussion going
Yes.
outside. There's food, tea and coffee out there. So join me in thanking Brian again.
Thanks a lot.
Translation is actually